In 2023, something invisible but catastrophically powerful struck our planet. It did not leave a crater or scorch the atmosphere, but it set off alarms in the most remote laboratory on Earth. This was not a rock or a comet, it was a ghost particle, a single high-energy neutrino traveling across the cosmos. For decades, astronomers have watched the sky with optical telescopes, but this discovery did not come from looking up. It came from looking down, deep into the Antarctic ice sheet at the Ice Cube Neutrino Observatory, where thousands of sensors wait in the frozen darkness for the faint blue flashes of particle collisions. Neutrinos pass through us by the trillions every second, usually completely unnoticed. But this specific particle was different. It carried an energy signature so immense and so precise that it defied the standard models of cosmic events. It simply did not match the profile of a dying star or a standard active galactic nucleus. When a massive star goes supernova, it unleashes a torrent of neutrinos, but their energy levels are well understood. The 2023 event spike was an anomaly, a data point that refused to fit the curve. For a moment, the high-energy astrophysics community was left staring at a mathematical impossibility. What kind of cosmic engine could accelerate a particle to these energies without the typical accompaniment of gamma rays or visible light? The silence in the electromagnetic spectrum was deafening. It suggested a source that was violent, compact, and completely invisible to traditional astronomy. Enter the theoretical physicists from the University of Massachusetts Amherst. In a groundbreaking paper reported in early 2026, they proposed a solution that drastically shifts our understanding of the early universe. They suggested that we did not just see a stray particle, we witnessed a violent death. Their hypothesis is that this neutrino was the final scream of a primordial black hole. Unlike the stellar mass monsters we usually study, these objects were not born from dying stars. They were forged in the chaotic, high-density plasma of the very first second after the Big Bang. These ancient remnants are microscopic compared to their stellar cousins, some no larger than an atom but containing the mass of an asteroid. For billions of years, they have drifted through the cosmos, slowly evaporating through a process known as Hawking radiation. Stephen Hawking predicted that black holes leak energy and lose mass over time. As they get smaller, they get hotter, radiating energy faster and faster. But the UMass team suggests a twist in this final phase, involving a specific state called quasi-extremal. A quasi-extremal black hole spins at the absolute limit of physics, often carrying a significant electric charge. As it shrinks, it does not just fade away into nothingness. Instead, it reaches a critical point of instability, a threshold where the laws of thermodynamics trigger a catastrophic release. It implies that the object doesn't just evaporate, it detonates. This violent destabilization releases a concentrated burst of ultra-high energy particles. The new model predicts exactly the kind of solitary, high-energy neutrino that slammed into the Antarctic ice in 2023. If this hypothesis holds, that single data point is the first direct evidence of an event that has only ever existed on chalkboards. It would mean we have observed the death of an object that has existed since the dawn of time, offering a direct window into the conditions of the Big Bang. The implications are staggering. If these explosions are actually happening, it validates Hawking radiation in the most dramatic way possible. But more importantly, it suggests the universe is filled with these ticking time bombs, hidden in the darkness between the stars, waiting to reveal themselves. But proving this was a black hole explosion requires more than just one particle. We need to understand the mechanism of the collapse itself and how it connects to the biggest missing piece of the cosmic puzzle. Next, we will break down the physics of this violent evaporation and why it might finally solve the mystery of dark matter. To understand how a subatomic particle hit Earth with the force of a falling anvil, we must rewind the cosmic clock. We bypass the formation of stars and galaxies, traveling all the way back to the very first violent moments of existence. In the chaotic fraction of a second after the Big Bang, the universe was a boiling sea of density fluctuations. In certain pockets, matter was so compressed that it collapsed under its own gravity without ever forming a star, creating primordial black holes. These are not the supermassive giants anchoring galaxies, nor the stellar corpses left by supernovae. These are ancient microscopic artifacts, some no larger than a proton, yet packing the mass of a mountain, drifting silently through the cosmos for nearly 14 billion years. According to Stephen Hawking's famous prediction, these objects are not truly black, they leak radiation. Quantum mechanics dictates that particle-antiparticle pairs constantly form near the event horizon, stealing tiny fractions of mass and causing the black hole to slowly evaporate over eons. For a standard black hole, this process takes longer than the universe's current age. However, the smaller the hole, the hotter it gets, and the faster it radiates away its mass, eventually leading to a runaway release of energy known as Hawking radiation. Physicists from UMass Amherst introduce a game-changing variable, the quasi-extremal state. They propose these primordial remnants aren't simple spheres, but possess extreme properties, specifically intense electric charge or rapid angular momentum, spinning at the absolute limit of physics. This extreme spin acts like a cosmic brake, stabilizing the black hole and dramatically slowing its evaporation. It allows these microscopic monsters to survive far longer than simple thermodynamics would suggest, preserving them from the dawn of time until the present day. But nothing lasts forever. Eventually, the black hole sheds enough charge or spin that it loses stability. When this threshold is crossed, the braking mechanism fails catastrophically, and the remaining mass is converted into energy in a split second. This is not a chemical explosion. It is a violent rupture of space-time. The collapse releases a sudden, concentrated burst of ultra-high energy particles, a death scream from the early universe that travels unimpeded across billions of light-years of void. This fits the 2023 anomaly perfectly, a single high-energy neutrino arriving without the mess of a supernova. It suggests we didn't just see a random particle, but the final, violent moments of a primordial object that has existed since the beginning of time. The research team argues that observatories like IceCube in Antarctica are already sensitive enough to detect these signatures. They calculate a staggering 90% probability that we will definitively confirm another one of these explosions before the year 2036. Verifying this would be a monumental triumph, providing the first direct evidence of Hawking radiation. It would prove that black holes can die and that the universe is littered with these tiny, ticking time bombs waiting to signal their presence. But the implications go beyond proving an old theory. If these objects exist in the numbers predicted, they solve a bigger problem. We wouldn't just be looking at explosions, we would be looking at the invisible scaffolding holding our galaxies together. If these primordial black holes are real, they are the perfect candidate for the missing mass of the universe. Next, we will explore how these exploding relics might finally unlock the identity of dark matter and change our understanding of cosmic gravity forever. This single neutrino might be the key to identifying the invisible mass of the cosmos. For decades, we have searched for dark matter, the mysterious substance making up most of the universe's gravity, assuming it was some exotic, undetected particle. But this explosion suggests the answer has been hiding in plain sight as ancient, invisible black holes. If primordial black holes actually exist, they solve the biggest crisis in astrophysics instantly. These objects are simply dense pockets of matter formed during the chaos of the Big Bang. They populate the halos of galaxies, exerting gravity without emitting light, fitting the exact description of the invisible scaffold holding our Milky Way together. The 2023 event provides the smoking gun we have been missing. Until now, these objects were mathematically possible but observationally silent, ghosting through our detectors. But the specific energy signature of that high-velocity neutrino indicates a violent death, proving that these objects are not just theoretical constructs, but active, dying inhabitants of our solar neighborhood. This brings us to a startling statistical certainty provided by the physicists at UMass Amherst. Their models suggest we are not looking for a needle in a haystack, but waiting for a predictable storm. Based on the sensitivity of current observatories, they calculate a 90% probability that we will definitively confirm another explosion by the year 2036. We do not need to build massive new supercolliders or launch futuristic space telescopes to find them. The data suggests our existing infrastructure, vast underground neutrino traps and orbital gamma-ray observatories, is already sufficient. We simply need to keep listening, analyzing the stream of cosmic rays for that specific, telltale burst of quasi-extremal energy. Confirming this discovery would do more than just solve the dark matter riddle, it would crown a scientific legend. It would provide the first direct, undeniable observation of Hawking radiation, the process by which black holes lose mass. Stephen Hawking predicted this evaporation half a century ago, and seeing a black hole detonate is the ultimate proof he was right. It rewrites the rules of thermodynamics in deep space. We used to think black holes were eternal prisons, but this evidence shows they are temporary engines of destruction. As they shrink, they get hotter and brighter, releasing their stored energy back into the universe, acting as batteries that have held the energy of the Big Bang for 13 billion years. These exploding points of darkness are essentially cosmic time capsules. Because they formed less than 1 second after the universe began, their interior structure, now being glassed outward, contains information about the conditions of the infant cosmos. Examining these particles is like reading a letter written by the universe moments after its birth. The implications for the standard model of particle physics are shattering. Finding a macroscopic object that behaves like a particle forces us to bridge the gap between relativity and quantum mechanics. This single neutrino is the first potential bridge across that divide, offering a glimpse into the unified theory of physics that has eluded scientists for a century. We are standing on the precipice of a new era in astronomy, shifting from observing light to observing fundamental destruction. Just as gravitational waves opened a new sense for humanity, detecting the death cries of primordial black holes gives us a way to hear the texture of space-time itself, unraveling at the quantum level. As we approach the 2036 threshold, the hunt intensifies. Astronomers are now recalibrating algorithms to filter out background noise, specifically hunting for the unique spectral fingerprint of quasi-extremal evaporation.
Every high-energy particle striking the atmosphere is now a suspect, potentially carrying the final coordinates of a dying primordial beast lurking in our galactic halo. The universe is far more volatile and ancient than we dared to imagine. We walk through a sea of invisible ghosts, remnants of creation that are slowly ticking down to detonation. The 2023 event was a warning shot, a brief flash in the dark, telling us that the missing pieces of our reality are finally revealing themselves. Subscribe to Quasar Quest as we track the countdown to the next discovery and analyze the raw data from the edge of the known universe. The evidence is mounting, and the next signal could arrive tomorrow. Join us and keep your eyes on the dark sky.